on the Riemann sum. I think for the most part, besides the fact that we haven't technically defined delta x to be b minus a over n, so I thought I wanted to do that as well.
They didn't go over that in the book, and I thought they were smart sport.
Apparently everyone was schmucked to Gerard.
Our book makes us think.
Oh, never mind. I take it back.
In the sense that they don't always connect the dots, right? I mean, I think that's probably one of the biggest descriptions of our book, in the sense that it gives you the information, but it makes you think for
Yourself.
Well, that's not why I'm buying the book. Depending on how
I guess it's good because then you learn how to like kind of not jump to conclusions, arrive to conclusions.
I have Miss D teaching that.
Miss D ain't always gonna be here. Imagine on his like on a calc final at like whatever UCLA. Hey Miss D, how do you what's the rule with maximum and minimum?
What about that one guy that was like, the teacher was like, you can bring anything you want, but it has to fit on one sheet of paper. And then like he brought his like brother who was like a math genius, put the sheet of paper on the floor and the guy stood on it.
Is that a joke or that really happened?
I guess that really happened. Mr. Crawford told me.
I think it'd be funny. I would laugh. But the kid would fail, but I would laugh.
No, I mean, well, what is the teacher going to do instead? No, probably not.
I mean, a good teacher would then hold up the piece of paper and then look at the kid and then be like, yeah, they have different volumes, doesn't it?
Oh.
How are they going to pick up the piece of paper if the kid's standing on it?
Oh snap!
How do you take it off the piece of paper? Be like, let's do a test to verify. And be like, oh wait, never mind.
Well, surface area it fits because we have varying surface.
Alright. Oh, there was a math test once I didn't even turn in.
Oh,
Miss D.
You
like
what?
Mr. Will's
I didn't even turn in.
You didn't turn in what?
I took it with me out of the room and I threw it in a trash can.
Oh, why?
Because it was just going to be painful for the teacher to grade, and he let the final replace the lowest test score. And I knew I'd basically get a 0 on the test. It was 2 questions, and I didn't know either one.
Wow, that's rough.
Proofs.
Oh, those are pretty
Not
easy.
geometry.
calculus proofs. There you go.
Not calculus.
Oh.
Is it like proving 1 + 1 proofs?
Had something to do with something being closed under something or others, probably.
Wait, how do you prove 1 + 1?
Don't worry, friends did that too. The same teacher.
I don't know what's right. I'm so
I've never written so much.
What's n? As you guys are writing.
Number.
Number
of
of.
subintervals.
And this, as n goes to infinity, as you're fitting an infinite number, as you're approaching an infinite number of subintervals fit within a finite space, what is occurring to the lengths of those subintervals? Yes, they're getting smaller. And the spiffy calculus term for it would be the partitions. The partitions are approaching 0. There technically is another very similar definition that has something to do with the partition approaching 0, which would be the limit as partitions are shown by double lines. Is it called a P? I don't know, something like that. But you could have the partition double lines as the partition approaches 0. That's another way of saying the limit as n approaches infinity. I just like the n thing better because we're thinking about n rectangles fit into n subintervals. I think it works a little bit better. But as you notice, C sub k is chosen arbitrarily in the kth subinterval, meaning in each of the individual subintervals, it doesn't truly matter which part we use, the left, the right, the midpoint, or some other arbitrarily defined point within. As the subintervals approach infinity, as the partitions approach 0, we're going to approach, and if it exists, arrive at the actual area. Real quick note, continuous functions are integrable? I really need to figure out how to say that word. That one.
Integrable.
That's another variation.
That's a fun word.
It is.
Say it that time after that.
Maybe tomorrow. So, Leibniz. Notation. All the easy stuff, right? So we have our integral. Here's a funny thing though. In calculus, Leibniz changed a delta x, delta which is Greek, to dx, d which is Roman, to talk about the differentials, kind of talking about the difference. Leibniz also took the Greek sigma, showing a summation for integration, and changed it to a Roman s, so the integral sign actually does come from an s for summation, but it's just been elongated so it's not confused with an actual s. Gerard, go ahead.
I hate being that guy. It's Latin.
Mm-mm.
No?
Sigma's Greek. Looking me up like I had.
Thank God, yeah.
There you go. Upper limit of integration is gonna be our B, lower limit is A, that was actually found by, was it Fourier? It's in the book, I think it was Fourier.
Actually, Fourier is the front part of the rich person's house.
Okay, it's spelled the same, Fourier. Yeah.
Never mind.
So we have the integrand, that's the function that's in between, we have the variable of integration, which is gonna be the dx, and we'll see the application as we go to antiderivatives, and then we are just talking about how to say the integral of f from a to b. Okay, so those are all notation-y things. Here's the definition, technically, and then here's the Leibniz notation for a definite integral. Both of them are signifying a finite area as long as the function can be integrated. Ooh, there can be infinite area? That's exciting.
Hours.
Question, how on earth could I ask you to use the graph to calculate the area?
Well, they integrate.
Ooh, the AP guys love this one. How do you integrate? Charter, we're not learning antiderivatives right now, so don't worry. But how could you integrate my ones that have integrated before?
Misty, I'm confused. Like, what are you saying? Like, we're not doing antiderivatives?
Because you don't need them, and actually, I'm trying to show you that you couldn't do this one,
Really?
not with integration.
No.
Why not? What would you be? Well, no, but it's a good discussion. What would you be?
You would be.
16 minus x.
Uh-huh. And so if, I'm just showing you something, Gerardo, but don't worry about it. 16 minus x squared, what would du be?
9 minus 2x dx.
Where's the negative 2 next to you?
What are you talking about?
Okay.
Oh, it's the one that you have to do
Because it
super
doesn't
creatively,
count.
So
right?
then maybe it's integration on crack, and we take that over, right? And then we say, okay, let's go
Integration of
ahead and,
crack.
Yeah,
It's
I
coming.
forgot about that. I
but
totally-
how would I solve for x? Because x would equal minus 16 divided by a negative, that'd be 16 minus u, plus or minus square root 16 minus u.
What just happened?
You know what I mean?
Yeah.
And then if you plug that in there, and then you have square root of u, and then it's not getting any better. Okay? So
Wait, what?
integration, not the answer. We'll get there.
That's not the answer.
It's not the answer. So why did I say use the graph? How on earth are you supposed to know this graph?
It's a circle.
Whenever you have y is
It's half a
equal to the
circle.
square root of r squared minus x squared, it's always a circle with a radius of r. Struggle. So, why am I just drawing the top half? Why am I only drawing a semicircle?
Because it's not plus or minus.
Because it's a principal root, it's only the positive square root, plus and minus would be the actual entire circle. So then if I'm asking for the area from, careful,
Negative
how much of the
4
circle do I
to
want?
0, a quarter.
Can't you do like area of a sector?
Don't need to,
But why? It's just.
it's a quarter of a circle,
The
so I just do
radius.
1/4 pi r squared. I could do area of a circle if I needed to, but I don't need to, does that make sense? So I can just say the integral from negative 4 to 0 of square root of 16 minus x squared dx is equal to 1/4 pi r squared.
Yes. You want it.
So pi 4 squared, pi times 16, which equals
4 units.
4 pi units, yeah, they didn't give us something. Now, why did I show you this example? Because even after you get really good at antiderivatives, and even after we go over a whole other chapter of all the different new techniques of integrating harder functions, ooh, that sounds fun. This one still is not one that we would ever want to integrate. Gerardo.
Why is there a differential there? Just out of curiosity. I never understood that.
dy dx. You have to multiply the dx over. Right?
Yeah. dy dx is equal to the square root of 16 minus x squared, so if we do want to integrate and get back to y, we separate.
You have to integrate.
we
Okay.
need to get y terms in terms, we have to get y stuff on one side, x stuff on the other, and then we start integrating and get to our y equals and then our blah blah blah. Let's see, does that make sense?
Our bookends.
Exactly. If our bookends aren't there, it's not legal to integrate yet, right? Separable differential equations? Coming, not yet. Quick properties of definite integrals. Technically, you have not seen, well, okay. In this book, it has not been introduced yet what to do if there's area above and below. We've only talked about area above. So then, if we're thinking just in terms of areas and not antiderivatives yet, then we can say the integral from a to b of f of x dx is going to equal any areas that are above being positive minus any areas below being negative. It's not that area ever in and of itself is negative, but what it represents might need to be subtracted. So then we think about it as a negative, to be completely honest. And the example for this one will be fairly close, or fairly quick. However, if we were given the function y equals sine of x, and I'm not making you guys right now think about antiderivatives and how the sine comes from a negative cosine and thinking between pi and 0 and doing the fundamental theorem of calculus. Let's just say we take the fact the integral of sine of x dx from 0 to pi is 2. Okay, let's just take that fact. This area is 2. Okay? And with this idea of definite integration, area above being positive, area below we're representing as a negative, just thinking about how you can have positive displacement, or positive, I should say, total change, and then you can also have negative total change. What if I was to give you, can I dual page it and I still see it? Maybe not. What if I was to give you some of the following?
Oh, gross.
We're not going to necessarily work through all of them, however, just kind of think about the ideas.
Oh, these are questions.
What if I was, what if I was to ask you between pi and 2 pi?
That would be 4. No, because negative. So that would be
Negative 2.
Just between pi and 2 pi, negative 2. So just the lower portion, does that make sense? Not from 0. So that'd be negative 2. Because then this would go below, and then it'd have the exact same area because it's a symmetry of sign, but it would be negative instead. How about from 0 to pi over 2?
1.
Wait. If it's 2 minus negative 2, wouldn't it be positive 4?
No.
No.
From pi to 2 pi, that's what George was
Yeah.
doing. He was doing it from 0, but just pi to 2 pi.
it's
So you have to zoom in. Now from 0 to pi over 2, Amanda, why 1?
Remove half.
It's symmetric and it's exactly half, so we could say that is equal to 1. How about from 0 to pi of 2 sine of x?
Over 4?
Yes, because you could pull the 2 out. Constants can come out of integration, or at least be regarded later like differentiation, so we get 4. Negative pi to pi.
0.
0.
There is no 0.
Why is it sine of u?
Just because.
It could be sine of anything, sine of 5x dx, sine of 3x.
That's funny though, that's the only one that's different.
Yeah. But it's because it's du. If it was a dx, we'd be in trouble, because then we'd have like a u prime that offsets it and it would be different. Cosine of x dx from 0 to pi.
Ooh.
0.
Yes. Think about cosine. Sine has a symmetry, but so does cosine. And so if sine's area is 2, then I could also say that cosine's area from negative pi over 2 to pi over 2 is 2 as well. But what are they asking? What are the bounds?
0 to pi.
Yeah, so they're asking, they offset, so it'd be 0. Does that make sense? Okay, so what if I was doing sine of x dx from 0 to 2 pi?
0.
There it is. 0. How about, 2 plus sine of x?
4. No.
2, because you'd have to get a 2x.
Well, 2 to pi.
I'm thinking, is it 6?
That's pi. So it's 2 pi, 4 pi.
No,
Is it 6?
close.
8?
Why?
Oh, because pi. I see. Because sine of x, because you can do a different
Sine is
integral of 2 and the integral of
Yeah.
sine of x.
But then you can
That's what I
also
was
think
doing.
about, that the
Um,
x-axis moves down 2, right?
Wouldn't that just be 4 pi?
So here's the x-axis, right? So we have this area of sine, but what do we have underneath that? A rectangle. And what's that rectangle gonna have? A base of pi and a height of 2.
And so we integrate.
This whole thing got shifted up 2, so the x-axis is now down here, so I can say I have my little sine, my little top knot of 2 still, but then I just have a plain old rectangle down here. And that rectangle is gonna have, 0 to pi, it's gonna have a base of pi, and it's gonna have a height of 1.
There we go.
Right? So we can just say,
I multiplied them for some reason.
hmm,
I got 4 pi.
You can, it's like if you have 2x and 2, you can just, 2x plus 2, you can do 4x.
Yeah. I don't know. I don't know.
it's okay. It happens. How about sine of x minus 2 from 2 to,
Boy.
Yeah, that's what you
That's
think about the bounds.
translation
Wait.
to the right, right?
Think about the bounds. Sine shifts 2 to the right, and what happened to both of my bounds, 0 and pi?
shifted to the left.
Right.
To the right too.
But it's.
So it's the
Oh,
same.
it's not a.
Two. Uh-huh.
So the function shifts 2 to the right, the bounds shift 2 to the right, well, it's the exact same thing, sweet, 2. How about, sine of x over 2 from 0 to 2 pi?
Question.
Think about where the bounds are still technically doing.
0 to 2 pi 6 0.
So I could say it's from 0 to pi of sine of x. In essence, I could kind of think about u substitution. I could say if u is equal to x over 2.
Du would equal to.
I could change my bounds to be from 0 to plugging in 2 pi of sine. Oh, now I don't like this anymore. Struggle.
Is it 1? Is it 1 or so? No.
I thought it was going to be 2.
Well, if that's
Sine of
right,
u
then
du.
Sine of u du is 2.
2.
No, it's 0.
1.
No, it's 2. Yeah.
Times 1/2 is 1.
The math is showing it as 1.
But the answer is
In my head, I thought it was 2. I thought that's where they were going. I mean, we could plug and chug it into a calculator if we really wanted to. I mean, we could go ahead and do u is equal to and then do cosine. Be negative cosine of u. So negative cosine of pi, which would be negative 1. So negative 1, positive 1. And then cosine of 0 is 0. I think it's positive 1.
0 to pi, right? Okay. That's
Yeah, 0 to 2 pi of x of
0. 2 pi.
What? And go to the next
This
one.
thing lied to me. Trace your answer.
maybe radians.
Yeah. I haven't read this.
1 for me. Thanks. I'm pretty sure it's 1. But the sad thing is we had to use techniques that hadn't come into play yet. I'll struggle.
Apparently
If you
it's
think about
invalid.
this being a
Oh, I
dilation,
got an idea.
right?
I was thinking it would be 0 because it's from 0 to 2 pi. So that those are going to cancel out
That's what I
from
thought.
0 to pi and pi to 2.
Yeah, but remember the period changes because it's x over 2.
Oh, okay.
Does that make sense? So it's
Yeah.
going to repeat twice as often? Twice as often.
It's 4.
just-
My calculator is giving me 4. Sine 2 pi over 2.
This is why I like trig.
Well, trig derivatives are pretty fun, but this is starting to kill me.
Oh, cosine of 0 isn't 0, it's 1.
Mm-hmm.
Stay right there. So I do positive 1 plus 1, that'd be 2. Wait, 2 times 1 half.
It's 2 pi, it's 0 to 2 pi?
0 to 2 pi sine of x over 2 dx.
Which is 1/2 be 2, because du equals to 1/2 dx, so dx should be 2 du.
You before,
Yeah, I
right?
gave you.
Oh, thanks, Jackie.
Oh,
I didn't solve it.
Jackie,
I
come
just plugged
clutch.
in.
That's why he's a thinker.
Exactly. There we go. Alright, all better. And Gerardo, you got to see us solve it. What? Go team. Okay.
But there's a good antiderivative though.
Yeah, I know. That's why I was like, I wasn't sure how they expected you to do it this one.
Okay.
Except to think about that it would be, I think where I was going before kind of makes sense, but I got a little confused. Because then this would be a horizontal dilation by a factor of 2,
Mm-hmm.
which means all of it would be stretched to, oh no, that would make, no.
This is why
I
math
don't
should
know,
be.
stretching the areas, that's getting a little too confusing, and we have better ways of dealing with it. So one more properties of definite integrals. Does a constant make a difference?
Nope.
Nope. So if I'm taking the integral of a constant function, in essence, I can basically say, remember what we did before, like with our constant rates, etc., that whatever c is, y is equal to c, that can be the same thing as our height, right? And then whatever our b is and whatever our a is, they're talking about it, and once again, in terms of area, I can say, I should have moved a little bit over. Oh, how did that get all attached all at once? I know. There we go. Without even talking about antiderivatives or talking about the fundamental theorem of calculus, with any constant function, we can say it's always going to be c times b minus a, because it's going to be base times height.
What is this elusive fundamental theorem of calculus? I've heard it a lot and I don't know what it is.
It's coming. It's incoming. It's coming. It's coming.
Like, whatever.
It takes the idea of an integral where area represents total change, and it takes the idea of differentiation backwards, and it puts the two together and shows how they relate.
That's the fundamental theorem of calculus.
Basically, that's what it does. Accumulator function. This is a little bit interesting. Accumulator function. You guys have seen the AP use him a lot. Just we haven't necessarily named him before. They like to go from a bound to a variable. They like to use FTC part 2 and have you like deriving both sides. But an accumulator function means basically you're keeping that x unknown, and you're saying from a to, and it could be a to, let's say a was like 0 or something, so it could be 0 to 2, 0 to 3, 0 to 4, 0 to 5, and as that expands, you're accumulating more and more areas, you're accumulating more and more change. We'll see that applied in just a second. And then discontinuous integral, what? Discontinuous? What?
Oh, I saw one of those over summer.
Integrable functions?
You can just like take.
Some discontinuous functions may be integrable as well? How does that work? Okay, let's start one thing at a time. Find the output from a pump producing 25 gallons per minute during the first hour of its operation. Wait, what's its rate?
25 gallons per minute.
Constant. So if its rate is constant, can't I just use old-fashioned gallons per minute and I'm multiplying it by what?
60.
60 minutes, because it's 1 hour.
Yeah.
What am I doing? I'm doing a change in time times the rate. I'm doing basically a snazzy, nifty-difty integral. So we were supposed to actually say what we were equaling. So that would end up being the integral from 0 to 60 of 25 dt. We're talking about time. And then we'll end up with 2560. Sixty quarters.
1500? Am I quick?
I should be able to do this faster.
Yeah.
0, 0, 3,
Yeah,
yeah,
1500.
gallons, right?
Because 5 times 25
Nice.
is 125, and
And
then
then
150 times
times
6.
12. I got
Oh, I
computed.
did 25 times 6.
Or 6 times
Plus
25 and
zero.
then plus 0.
I'm still writing the problem down.
Write the accumulator function, a of x as a polynomial in terms of x. I know a lot of you guys are like, psh, we're just going to integrate, but hold on. What's the idea of the accumulator function?
It shows like the area as a function of time, right?
Uh-huh. And if I think about 5 minus 2t, my ones that geometrically were having some issues, I struggle. What's going on?
5 minus 2t, it's up 5.
Up
and then
5, and
down.
can I have it coming down?
Yeah.
Theoretically, and I end it at whoever x is, and I start it at whatever 1 is. The question, how could I find this area as it keeps on getting bigger and bigger? I could say my base is equal to,
1.
let's just say it's a
X minus 1.
my base is x minus 1, and what's my height going to be? 5 minus 2 times whoever x is. What? And that's without doing any integrating in terms of antiderivatives.
Oh.
That's pretty snazzy. Anyway, I'm going to leave you guys with the discontinuous integrable functions and see how you're able to do. But I'll go ahead and as you guys leave, I'll solve these two so that you can actually go back and look and say, what? Ones with discontinuities can still have integration? Or areas under their curves? Bye guys, see you later.
Joyce, like, subscribe, leave a comment below.
Yeah.
Are you gonna meet tomorrow?
Yeah, it was supposed to be announced HTTP that didn't want
It's okay, it's still good.
to. We're gonna have an announcement tomorrow. Like, there's one for tomorrow too, so as long as.
Oh, is that why you were asking how you put in?
But like Wednesday doesn't work, so there's 10 to 12. Thursday
Friday.